Okay, hi everyone. Sorry for the technical challenges. My name is Erik Malmi, and I'm going to present you a text editing method that we've developed together with my colleagues at Google Zurich. But before I go into the method itself, let me give you some background. So as we heard in the excellent keynote this morning, sequence-to-sequence methods have really revolutionized machine translation. And not only machine translation, but actually they've become sort of the standard method for many other tasks, especially this kind of monolingual machine translation tasks, where your source text and the target text have the same language. So to give you some examples of cases where SIG models are often used, abstractive summarization, sentence fusion, split and rephrase, and many other tasks. And in our work, we focus specifically on this kind of monolingual machine translation tasks. However, SIG-to-SIG methods are known to have some limitations, even though they show good performance for machine translation. So these are often, one well-known problem is hallucination. So these methods invent new information that's not grounded in the source text. Also, they're very, require lots of training samples. And for machine translation, you might have millions or hundreds of millions of parallel sentences, but many of these monolingual tasks, you don't simply have that training data available. And finally, these can be quite slow at inference time, which makes it harder to productionize these models. Also, one of the sort of key characteristics of monolingual tasks is that usually there's a high overlap between the source and the target sentence. And to capture this observation, what people have done, they've developed different kind of copy mechanism to make it easier for the model to copy words from the source. But even with these mechanisms, the models are still susceptible to these limitations like hallucination. So to dive into one of the applications a bit more closely, if you're doing text summarization, you might train a SIG-to-SIG model to do it abstractively so that it paraphrases some of the stuff. But what people actually commonly do for summarization is to do it purely extractively. So rather than rewriting it from the scratch, trying to predict which tokens to keep and which to drop. And this makes the learning task much easier. But on the other hand, it makes the model less expressive. So you cannot produce arbitrary summaries with this approach. Moreover, if you want to apply it for other tasks, extractive method is not really an option, because for tasks like sentence fusion, you really need to be able to add new words or phrases to be able to fuse sentences in a reasonable way. So kind of the focus of our work has been, can we find some kind of middle ground between the purely abstractive and the extractive approach, so that we would still have a reasonably easy learning task, but we would also be able to insert some stuff. And to this end, we've developed a method we call laser tagger. So laser tagger simplifies this problem into a prediction of edit operations. So for each token in the input text, we predict an edit operation, which can be either keep or delete. But additionally, we allow the model to predict that certain phrase should be added before a given word. And to summarize some of the highlights from the paper, so we studied 4 different tasks. We got new state-of-the-art results on 3 of them. One very nice thing about the method is it's super data efficient, so we can train reasonable models with as little as a few hundreds of training samples. And it's also much faster at inference time than a comparable SIG-to-SIG method. So how does the method work actually? We get an input sentence, we encode it, and then we predict a tag which represents an edit operation for each of the tokens in the input sequence. Then finally, we apply these tags so we realize the output. And in this case of a simple sentence fusion, we could, for example, predict keep for all the tokens except for the period, which in this example, the model predicts to delete and add phrase and he before the deleted period. Then it drops during and gets the output. Turing was born in 1912 and he died in 1954. So the next question is, what can the model add between the different tokens? And we decided to take sort of conservative approach that we don't let the model generate whatever it wants between the tokens, but we define what we call phrase vocabulary. So this defines all the possible phrases that the model is allowed to add. And this would contain things like discourse connectives and pronouns, for instance, for the task of sentence fusion. The good thing about this is that it guarantees us that the model is not able to hallucinate arbitrary stuff between the input tokens. So how we sort of learn or optimize this phrase vocabulary. So we define an optimization task where the goal is to minimize the size of the vocabulary while maximizing the number of training examples that can be reconstructed with the given phrases. And this turns out to be an NP hard task, but a simple greedy method works quite well. So what we do is that first we align all the sources with the targets. Then we find all the added phrases by looking at what is not covered in the target. So in this case, it would be the phrase "and he." So we do this for all the input, for all the training samples. Then we simply rank the phrases based on in how many training samples they occur, and we take the top k phrases added to the input. And in the experiments, we used a phrase vocabulary size of 500. Okay, so given this phrase vocabulary, what you need to do to use laser tagger. So first, you convert all of your training target texts into target tag sequences. And each tag, as I briefly mentioned, so it consists of either keep or delete, the base tag, plus an added phrase, which can also be empty. And then additionally, we introduce a tag called swap. So swap reverses the order of two sentences. This is especially useful for the sentence fusion task. Okay, then we train a tagging model to predict these edit operations. And finally, when we use this at the inference time, so we predict the operations and we realize the output. This involves applying the edit operations, but also doing things like fixing capitalization around changed sentence boundaries. And here's a bit more complex example of what you can achieve with this type of editing approach. So again, if you're doing fusion and your sources are Dylan won Nobel Prize, Dylan is an American musician. So using the swap operation to swap the sentence order, you could get an output like Dylan, an American musician, won Nobel Prize. So the second step was training a tagging model. So what the model actually looks like, what we found to work best is a transformer encoder. But on top of that, so people have previously tried plugging things like CRFs or LSTMs on top of BERT, but we found that the simple one-layer transformer decoder got us the best results. And this is used to capture sort of the dependencies between the output tags. Right, so in the experiments, we compare 3 methods in addition to the previous work. So first is this autoregressive variant of laser tagger where we use BERT plus transformer decoder. The second method is a feed-forward version where we just use the vanilla BERT model, which is fine-tuned on the tagging task. And we compare these two approaches to a SIG-to-SIG model. We initially tried many different transformer models, but the best results we got with a 12-layer transformer where we initialized the encoder with a pre-trained BERT checkpoint. And we run experiments on 4 different tasks, but now in the interest of time, I'll just show you results on sentence fusion. So this is done with a recently released DiscoFuse dataset. And here, compared to the previous transformer approach, we obtain an improvement of about 2.5 percentage points in terms of exact score, the accuracy. We also see that the autoregressive version works slightly better than the feed-forward, but the difference is not huge here. And also, actually, the sig-to-sig method works really well, so it gets almost the same performance as the lazy tagger autoregressive variant. What is perhaps more interesting is that if you start subsampling your training data set, so you see that when you have the full data set, there's no big difference, but when you go below a few tens of thousands of training samples, then you see that the sig-to-sig model is not anymore able to learn any reasonable model. Whereas the tagging approach actually performs very reasonably even if you have few hundreds of training samples. Okay, so I also mentioned that we get some improvements on inference time. So here we ran inference on GPU, and you can see that the feed-forward variant is about 2 orders of magnitude faster than the sig-to-sig baseline that we compare against. The autoregressive variant is also faster, but there the difference is not as big. So finally, we also wanted to do some kind of qualitative analysis of the errors that we see in the predictions of the different models. And we categorized these errors into, I think, 7 different error types. So I'll briefly go through some of these. So first error type is imaginary words. And this is quite frequent with sig-to-sig methods when you have some very frequent input tokens and the sig-to-sig might just replace one of the word pieces there to make it completely unsensible. Whereas the lazy tagger is really immune against this type of errors because it doesn't have these weird words in the phrase vocabulary. Also, sig-to-sig methods sometimes repeat words, and they tend to sometimes predict the end of sentence token too early, which is not likely to happen with the tagging approach. There are some issues like coreference issues and misleading rephrasing, so dropping a negation, for instance, that can happen with both of the methods. And finally, one of the error types that is more characteristic to lazy tagger is that one of the tasks we studied was sentence splitting, and there we saw that the tagging approach sometimes inserts the sentence separator, but it doesn't really rephrase the 2 sentences like the task usually involves, unlike the sig-to-sig approach. Okay, to briefly mention some of the related work. So actually, very recently, independent of our work, there have been 2 very similar approaches proposed. One in ACL this year called EditNTS, and one actually at the same conference called Pi. Also, there's some work on adapting transformer to do both keep and both deletion and insertion operations. And then there are also some work on morphological reinflection that uses somewhat similar editing models. So to conclude, we propose lazy tagger, which is a high precision model that's not as susceptible to hallucination as the sig-to-sig models tend to be, and it's also faster at inference times. And these characteristics make it much more suitable for making models that run in production in real time. One nice thing also is that it's very data efficient, and actually what we found out is that in the cases that we don't have any training data or easy way to collect it automatically, we can even crowdsource the training target. So we ask, for example, some human crowd workers to fuse sentences, and then we train a model on a couple of thousand of human created targets. Okay, some limitations and things that we're currently working on. So currently we've only tested this for English. To go for some morphologically richer languages, it probably requires some modifications to the model. And also, if you need to do heavy reordering of the words, that's currently not supported so well. So these are things we're looking into currently. And we made the code available, so feel free to try it for your own task. Thank you very much.
We'll have time for 1 or 2 quick questions. Any question from the audience? If not, I have one quick question. Do you have thoughts on how does this compare to these neural finite state transducer model, since it's also like insert delete?
So I'm not sure if I know exactly the methods you're referring to.
So they basically, it's the finite state transducer, but people can use neural networks to parameterize them so that you can get a better estimation on when do you want to delete or cut. So basically, it's the same operations that similar to your operation set. The only thing I can see is like the swap cannot be easily done by the.
Yeah, that's something we should probably look into. I think we've actually internally tried one model that's based on finite state transducers, and it worked quite well, but I don't know, for example, so here we're able to leverage pre-trained BERT models, and it improved a lot against some of the simpler sort of tagging architectures that we tried.
I see. Thanks.
Thanks.
Let's thank the speaker again.